Hi everybody, Professor Ghassemi here. In this component of the lecture, we'll be discussing dependency parsing. So far we've been thinking about language statistically, or in this lecture series, we started thinking about language as a set of rules that are specified by a context-free grammar. Now, the context-free grammars are very simple and elegant. Why? Because we can enumerate the rules. It's sort of easy to think about, easy to write out as software, and so on. Well, there are some deficiencies of context-free grammars, such as the points that we spoke about in the end of the last component of the lecture. And they're also not the only way to represent information about the structure in a sentence. We could, for example, take advantage of the fact that words really, in a sentence, kind of, in a graph sense, depend on other words. So for example, here in this sentence, I prefer the morning flight through Denver. Prefer here sort of depends on the word flight, right? So the preference is really referring to the word flight. And the word flight is referring to the word morning, right? So there's basically logical links that I can draw that connect these words directly in the sentence that does not rely on the specific order of the words in the sentence. When we choose to try to represent things about the grammatical structure this way, it's called dependency parsing. And these dependency grammars, which are what consequently come out of dependency parsing, just provide another representation of language as a graph, where the nodes are the words and the edges are the dependencies between those words. So in these formalisms, the syntactic structure of the sentence is described solely in terms of the words and a set of directed binary grammatical relationships. So that is to say, there's no parse tree here anymore, right? It's just, I have these, in this case, 6 words. These 6 words can have an arrow from one word to the other. And anytime I draw an arrow from one of the words to the other, I have to specify what the relationship is between those 2 words, okay, or why I'm drawing that arrow, okay. These relationships are usually depicted as labeled arcs from what they call a head to a dependent. So the head is sort of the root word, the boss word in the relationship, and the where the arrow ends is the one that depends on that root word, okay? So when you have a dependency grammar approach, it obviously abstracts away the word order information, because unlike the context-free grammars where we were sort of stepping through the sentence from left to right in order of the words, you don't have to do that when you have a dependency parsing approach. Okay, and so it's particularly important, or these approaches, I should say, of dependency parsing have become particularly important in a lot of contemporary speech and language processing systems for the problem of coreference resolution, which is where you have a sentence such as, I voted for Nader because he was the most aligned with my values, she said. Coreference resolution is the problem of figuring out that she, in this case, refers to my, he refers to Nader, and my refers to I. So figuring out that there are these dependencies between the words in the sentence, which is the coreference resolution problem, is typically performed using dependency parsing techniques. It's also useful for other kinds of problems such as question answering and information extraction, but I think coreference resolution is sort of the big one. Now, dependency structures are represented by directed graphs, and those directed graphs have to satisfy the following 3 constraints. First is that there is a single designated root node that has no incoming arcs. You say this is sort of the master of the sentence, the master word, the root word of the sentence. And you have to specify which of the words here is going to have that root node attached to it. And you can't have anything coming into the root. or any of the things that the root is sort of attached to. So notice, to be very clear, root sort of attaches to prefer, but prefer doesn't have an input arrow from any of the other words in this sentence. Okay, so that's one of the qualities that have to be satisfied. The second is, with the exception of this root node, each vertex has to have one and only one incoming arc. So you can't, for example, have two incoming arrows to the word morning. And you'll notice when you just glance across these that each of the words only has one incoming arrow coming into it. Okay, and the third is that there's a unique path from the root node to each of the vertex in V. So what that means is that I have to be able to move from, for instance, this root prefer, and I have to be able to traverse this so I can get to any other word in this structure. Let's say, I wanted to move to the word Denver. I would need to hop from prefer to flight, and then from flight to Denver. Okay, if I had drawn my dependency structure in a way where it was impossible to navigate from prefer to Denver or any other word in this sentence, then I would have violated one of the requirements of creating a dependency structure. Now, the great thing about graphs is that you can represent them by adjacency matrices, or because we have multiple classes that the relationships can hold, we might call it an adjacency tensor when you want to do analyses. So for instance, we could have a three-dimensional matrix here, and each of the two-dimensional slices that we're observing here could refer to one of the kinds of relationships that could exist between the words. And we could put a 1 when that relationship exists from one word to the other, and we could leave it blank or 0 otherwise. So in this case, for instance, we see that flight goes to morning. So we say, similarly, we update this matrix to say that flight goes to morning, and we're going to represent that by a 1 in this position of the adjacency tensor. And flight also goes to Denver. And so we similarly represent that here. And we could have another slice of this adjacency tensor that maps out which of the words is having the root relationship, such as through a representation like this. And this is obviously one way to do the representation. Another way is to actually add a root as an actual term in this matrix. So I would have, for example, root, I prefer the morning flight through Denver, and then up here I'd have another column, root, I prefer the morning flight through Denver. So I'd basically increase the number of rows and columns in here by 1 so that I could map it out that way too. Okay, now there are multiple algorithms that generate dependency trees from your data. There are 2 that I'm going to mention, one of which I'm going to go into in some level of detail. These are transition-based approaches. And I'm going to talk briefly about graph algorithm-based approaches, but I'm not going to go into a lot of depth there because I think we don't really have the time for me to review the fundamentals of how to do analyses on graphs. And I don't want to sort of overwhelm you with some of those methods. So we'll stick to the transition-based approaches for the purposes of the lecture, and I'll just mention the graph-based approaches in case you're interested in looking into those on your own time. Okay, before we jump into it, note that some algorithms that handle dependency parsing are projective. You're going to see this word come up if you read our textbook or you look at papers. Now, all it means to be projective is that the edges in the graph are not allowed to cross. So this is an example of something that's not projective, right? Because saw crossed over, one of the lines from the other, the other parts of the graph. If it was projective, you'd never have these cross points like I'm showing here, or I guess this is the cross point in this particular graph. So we'd have to remove this if we wanted to do that. One very simple way would, if we had saw point to A and dog point to yesterday, that would solve the problem. That might not be the correct way to represent the dependencies, but a non-projective method sort of would be able to catch a structure like this, whereas a projective method would struggle because it forbids the crossing of these arcs. Okay, so just bringing that to your attention as in case you encounter the term projective. Okay, now when we speak about the transition-based approaches to developing the dependency structure, there is what's called the arc standard approach to solving the problem. And what we do here is we step across n words in a sentence that we're interested in generating a dependency relationship between from left to right. And for each word, wi, our parser can do three actions. It can either put a word in a stack over here for analyses. It can assign a word from the top of the stack as the head of the previous word, or it can assign a word from the previous word in the stack as the head of the top word. So basically, it can figure out a way to draw for these two items in the stack, what's dependent on what. Okay, and so let me sort of take you through an example here. The first thing we might do in this case is if we had an input buffer that was filled with root, book me the morning flight, is we would shift the root word onto the stack. Okay, well, the stack doesn't have anything in it yet, so we obviously still need to continue shifting. So the next thing we would do is we might put book onto the stack. And so now book is there. Okay, well, one of the things that is the terminal condition for these kinds of parsers is that the last word, the only time you want to do the analysis of the root is when you sort of get to the end of the, when you get to the end of your input buffer. So because we still have things in our input buffer, we're also going to shift in next word, me. And now we have enough words that we have more options, right? We could either continue shifting words in, or we could try to assign a relationship between me and book. The way that these parsers do this, figure out, given the state of the system, so given what's on the stack and given what's on the input buffer, you know, should I draw an arrow here from me to book, from book to me, or should I shift? That's usually handled through supervised machine learning algorithms. So for the purpose of this example, just understand that this parser, let's say, is a trained model. It knows based on the state of the system how to go about choosing the next best action, just for the purposes of the example. Okay, so let's say that it looks at the data and it says, okay, well, it seems that I need to draw an arrow between book and me. And this, because we're assigning a previous word in the stack as the head word of something at the top of the stack, this is called a right arc. Okay, so it adds that relationship. It pops the word me from the stack because that was what was being pointed to, and it then continues on with its operations. And the next operation we might do, for instance, is shift onto the stack. So we might start adding more words onto here. And then we would perhaps do more relationship assigning. So we might say here that there's a left arc relationship that exists here. There's another left arc relationship that exists here, which, as you can see from the arrow's direction, just says that, you know, flight sort of points in the graphical sense to morning and flight points to thee. And we might say that there was a right arc relationship between book and flight. And then finally, because we're at the end, we know that root must refer to book, and we've completed our parsing. I want to make very clear, I'm trying my best to decouple how the parser goes about generating these three, you know, actions, which I'm going to talk about in a minute, and how you move from the contents in the input buffer and use that in a stack to analyze sort of two words at a time, so that you can predict what the relationships between the words might be. This process, assuming that the parser is already trained, is what the standard arc approach is. Okay, so when you hear people refer to it, this is what they're referring to. Okay, obviously, when you have that set of relationships that the parser outputs, that's what you use to draw the dependency graph that you see here. Okay, well, the most essential piece of this algorithm that was missing was, of course, the parser. And the state-of-the-art transition-based systems use supervised machine learning methods to train classifiers that perform that parsing. So given some appropriate training data, these methods are basically learning a function that maps from configurations to transition operators. Okay, so it's a standard, straightforward, supervised machine learning problem. Now, of course, if you're going to do supervised machine learning, you need data, right? And the data that's used to train these kinds of models comes from the Universal Dependencies project. And there are other tree banks that provide an inventory of dependency relationships that are generated by human annotators. So you can use those to train the model. Now, the second thing that I want to touch on just very briefly, and we're not going to go into a lot of detail about it, are the graph-based approaches for dependency parsing. Effectively, the way that these graph-based approaches deal with the problem is they treat, just as we did before, each of the words as a node, and they assign a score that says something about the potential dependency between each of the words inside of the sentence and each of the other words. So, book has a connection to all other words. That has a connection, and flight and route. And then what they search for is what's called the maximum spanning tree. That is the particular way of drawing the connections that will maximize the dependency score that's specified. The specific algorithm that's used for this maximization is called the Chulu-Edmonds algorithm. And I'm listing it here. It won't be required for anything we'll be doing in this class. I'm only just bringing it up so that you're familiar with it in case you become interested in dependency parsing and want to explore it some more on your own time later.